Welcome to the fifth installment of our Unit 3, where we've been talking about horizontal projectiles, and now we're going to talk about projectiles launched at an angle. All the properties are almost exactly the same. So for starters, examples of things that would be launched at an angle, we could have cannonballs are a common thing that we come across, golf balls, just about any sport where you're hitting something, the object will move as a projectile. So tennis, baseball, if you get the puck up in hockey, doesn't happen very often, but it does move as a projectile. So just as before, the horizontal component was constant, and it will always be constant. The reason it's constant is there's no acceleration horizontally. So the Vx is constant the entire time. Vertical component behaves just the same. It has acceleration caused by gravity. That the only difference from horizontal projectile problems is that instead of v naught y being 0, it is some number, which means the object will go up. It'll eventually hit a peak height where the vertical velocity is 0 meters per second, and it'll start going back down after that point. So it's just like when we've thrown a ball straight up and down, but now it's also moving horizontally as well. The same types of assumptions still work in our vertical direction. So all of those vertical assumptions about the velocity up equaling the negative velocity when it's going down at the same height, the time up to the maximum height is the same on either side, so it's just half the total time from one end to the other. So all those assumptions we've used before come back into play here for the vertical direction, not the horizontal direction, but for the vertical direction. So to solve these problems, what we do is we're giving an initial velocity that's at some angle. The first thing we have to do is get the horizontal and vertical components of that initial velocity. That's always our first step, and then from there, it is exactly like the horizontal problems where we look at horizontal values and then vertical values. So let's take a look at this example. So we've got Spencer, random Spencer, and kicks a soccer ball that was at rest, gives it an initial velocity of 7.8 meters per second at an angle of 32 degrees above the horizontal. If it eventually lands on the ground, again, some distance away from Spencer, how long will the ball be in the air? How high will it go? And then what is the range? Before we even get into those questions, let's set it up. So the first thing we want to do is draw a picture. Always draw a picture. And this is just so we can think about what the question is asking us. So we've kicked a ball, it's gone up and come back down. It was initially moving 7.8 meters per second and had an angle of 32 degrees. As soon as it's gone away from that very initial point, those two values start changing. It's at a different angle and a different velocity. So that is only at the very first immediate moment. First thing you got to do, don't even worry about answering A, B, and C. Find V naught x and V naught y. Don't even think about answering the problem until you've done this. So let's draw a triangle for our vector here that is V naught, and we're just going to work with everything's positive because we're not giving any other information to think otherwise. So we just have V naught x, V naught y, and our angle theta. So V naught x will be cosine because it is adjacent to our side. So we have then V naught times cosine of our theta. And then V naught y will be V naught times sine because we just use cos. So plug in our numbers, 7.8 meters per second times the cosine of 32 degrees. And we'll get 6.6148 meters a second. That'll be to 2 sig figs. and 7.8 meters per second times sine of 32 degrees, and that'll be 4.1334 meters per second, and again 2 sig figs. Okay, now we can look at what we can do to solve the question, because we can only work in x or only work in y. What we're looking for in a. So let's do a over here, and we are looking for t, and we know that the time in x direction is the same as the time in the y direction, so we can really make a lot of different approaches to this problem. A lot of different ways we can solve it. But if we start with our most commonly used equation, just see if we can use it at all. We'd have dy. dy is 0 because we land at the same height, so that's one thing. We do have that. We have ay, and we have v naught y. We just found that out. So we could use this equation. So let's just do that and see where we end up. So to do this, we have to make sure that, we have to say that this is 0 so that we can rearrange it. If we didn't say that was 0, you'd have to use the quadratic equation to solve this, which we don't really want to do. So to rearrange it now, our best option is to factor out a t, so that, because we have t in both terms, we can factor one of them out, and we get left with this expression. If you think back to your days in math and solving equations, this tells us that at one point time is equal to 0, and in the other side, I don't know why I wrote an equal sign there, and on the other side it would tell us that v naught y plus 1/2 at equals 0. So if you remember math, hopefully you can see where that came from. And now we just got to rearrange for time. So to do that, we'll end up with minus v naught y over 1/2 ay. Plug in our numbers. So minus v naught y, which we just found out to be 4.1334 meters a second over 1/2 times negative 9.80 meters per second squared. And we get time is equal to 0.84 seconds. So there we go. We just figured out the time by looking at the y direction. There's other equations you could have used to come up with time. So if you thought of a different way right off the bat, try that and see if it would get you the same answer. So now let's look for B. B is asking us for how high did the ball go, so we're looking for dy max. Now we have the full dy, but now we want to go how high was it to this point up here. To figure this out, we have to remember one of our assumptions that we can make, that Vy at this point would be 0 meters per second. This is the same as our assumption that we made when the ball was just going straight up and down. At the very top, that it came to a rest for a very brief moment. In this case, in the vertical direction, the same thing happens even though the ball keeps moving horizontally. So the horizontal velocity stays, but the vertical velocity eventually goes to 0, and then it'll start going back the other direction as the object comes back towards the ground. So that's the assumption that we have to use. To do this, our best option is to figure out, an equation that has Vy in it. If we can do that, that means we can get rid of something because it's 0. So one equation that we can use is this one, because that will give us the dy that we're looking for, because it's not 0, because we're looking at a different point in time. So if we rearrange for dy, we will get vy squared minus v naught y squared over 2ay. So that's 0. And we get negative 4.1334 meters per second. And that's all squared over 2 times negative 9.80 meters per second squared. And that'll give us a dy at the maximum height of 0.87 meters. Okay, we've done 2 of 3 questions. Let's take a look at C. C is asking us for what is the range. Range is just another way of asking for dx. Think of like a driving range. It's how far you're going horizontally from where you were. So dx is our goal here. Anytime you're in the x direction, we only have one equation, so we don't even have to think about what our equation is, and it will always be this. Let's make sure we have vx. Well, we have v naught x, but remember it is constant the entire time, so that is our number there, 6.6148 meters per second. We have the time, we figure that in A, so let's just plug it in and get an answer. So 6.6148 meters a second times 0.84 seconds, and that gives us 5.6 meters for dx. And that's the answer. So that's one example. I'm going to do a second video for this one as a second example so that the video doesn't get too long. See you in part 2.